Hi, good morning. My name is Logan Gard, and I'm the group leader for upcoming next week's Clapron experiment for Group 4, Section 3. All right, so the goal of the experiment will be to determine the latent heat vaporization of water utilizing the Clapeyron equation. Now, the Clapeyron equation is mainly used for phase changes. There's a few different variables or different versions there are. There are some for solid to vapor, liquid to vapor, but for this experiment, we'll be utilizing the liquid to vapor portion of that equation. As you can see above here, I said that we utilize the ideal gas law. I'm sure that most of you guys are aware that water, when it's in vapor form, is so low in density that it acts very similar to an ideal gas, which is why we end up using it there. I don't think I need to actually derive the equation. I think everyone pretty much understands. I plug and chug that in there. I used the Reynolds number 0.4615 for steam. I pulled it off the steam table because obviously when we vaporize water, it's going to be steam. So this is what we'll be working with. This is the full apparatus right here. That'll be the water that will be boiling over the hot, and then we'll actually have a centrifugal pump here pumping water through the system right here to pull air out of the actual beaker there. There's a compact computer system that's been recording pressures and temperatures at over a given period of time. For the initial setup, we're going to have to drain out all the pressure inside the flask to begin with using the centrifugal pump, which basically just pulls the water in and constantly cycles that, pulling air out of the system. Once it sets about as close to zero as we can get it, we'll go ahead and heat it up to about boiling, and once it's there, we'll make sure that everything's reading properly, and then going forward with the experiment, we'll take incremental measurements and slowly rise up the pressure. Once it gets to about ambient, we cut it off, go ahead and turn off the pump, drain it all out, and we're probably good to go. There's also the possibility of actually adding boiling beads, and that basically just stays the boiling point and make sure it's more constant and easier to work with. Okay, these are the possible results. I pulled these pressure and temperature changes from the steam table, so they're pretty much theoretical, but this is generally what we'll be seeing right here. As the temperature increases, you see the pressure will increase, and that's what we should mainly be expecting, this kind of reaction. Now, for the purpose of this presentation, I'm going to do some practice calculations right here. That's the beginning part of the equation, utilizing the ideal gas law, and this is me kind of just solving through it, making it more easier to work with. And for the purpose of the experiment, we'll be trying to calculate for the latent heat there, or enthalpy. I went ahead and calculated for 75 degrees because that seemed like a very simple time to take, and I could reference the steam tables to make sure I'm doing it right. As you can see, I got about 2321.37 kilojoules per kilogram, slightly off compared to what the steam tables are showing me. But just to reiterate, I also did 2 more calculations, and as the temperature increased, I started to notice a bit bigger and bigger gap each attempt, so I'm not sure how that's going to work out later on. And of course, with every experiment, there are some uncertainties need to be concerned about. I went ahead and put a general uncertainty equation at the top there. The way it works is x would be your variable that you are uncertain about, and the df over dx is just a derivative of that equation, reference what you're worried about right there. There's also some user error to be worried about, possibly the actual thermocouple not being fully submerged in the water, or a little jostling there, but all considered, that's pretty much all you need to be worried about with uncertainties. Any questions there? All right, well, thanks for your time.